Sorry, by the way, I'm not doctor. I'm just masters. Yeah. Okay. Yeah. So my voice is audible, right? Okay. So hello everyone. So I am from TCS. I'm Vishnu Menon from TCS India, and we are working in a research team. And our team is specifically like working on AI/ML applications and optimization applications in energy system, power system, smart grid, and at times smart buildings as well, and the related domains. So I will be presenting one of our work here. So this work is specifically about an large commercial enterprise which involves an electric vehicle fleet. So this fleets basically they are present at the enterprise for transporting the goods to different locations across the city. Yeah. So here this problem, I mean the enterprise, right? They includes different types of demand. Like first of all, the conventional building loads, like the HVAC loads and all, and even the electric vehicle charging demands as well. So here in electric vehicle, you have multiple options. You can charge from the enterprise, and you can even charge from the charging stations which are located at the different locations across the city. Like it can travel to some specific location while delivering the goods to the customer, and along the way it can charge, and so on. So the prices for charging at the enterprise will be different than the charging, I mean the cost at the charging station. So one way to, I mean, yeah, so we are concerned with the reduction of the electricity price at the enterprise. I mean, commonly like the enterprise purchases electricity from the local retailer at a fixed price, or using a TOU price or so. So one way to reduce the electricity price by the enterprise is by increasing the options for procurement of electricity from different options. So like there can be other options like solar PV installed at their own premise, or there can be a third party solar PV generation which is located at some other location than the enterprise, but it can have some one-to-one contract for procurement of the electricity. Then third option is that there can be battery installed at the enterprise. Fourth option is the electric vehicle battery itself. I mean, it can charge. I mean, it can charge the electric vehicle additionally than required for routing or transportation, and then discharge it into the demand of the enterprise itself. And even more, like there can be electricity market as well. I mean, this enterprise can participate in the day-ahead market and then procure some electricity. So right now there can be, I mean, if we have multiple options for the sources, I mean, from where you are purchasing the electricity, then there will be I mean, there are different prices for different, different sources. And so you would need a portfolio optimization to identify which is the best source at a given time. I mean, this portfolio optimization will also involve the risk. I mean, it also will take into consideration the risk in the market prices. I mean, because the market prices are the one which is varying for each and every time instances, and also in each and every day. So, so portfolio optimization is actually a standard technique which is existing. Uh, but now here, in case if we have a fixed demand, if we know the demand, then we can run the portfolio optimization very well. But here we have a different challenge, that we have electric vehicles as well, which can charge from the external charging station, I mean charging station as well. So the demand of the electric vehicle will be known only from the routing algorithm. I mean, we need to identify like which electric vehicle will be going to which customer station, and so the requirements of the different electric vehicle can be different, and it may happen that it is more cheaper to charge from the electric charging station from the external, I mean, because the prices may be low, and so on. Yeah. So here, yeah. So first challenge, as I already mentioned, that multiple sources with different prices and risk that can be taken into consideration by portfolio optimization method. So this portfolio optimization, just because of this, we don't know the price at the enterprise. So we don't know whether like it will be cheaper for the electric vehicle to charge from the enterprise or from the charging station. So because of that, if we are taking this electric vehicle routing also as a part of this portfolio optimization, there comes a cyclic dependency of this demand and electric vehicle charging cost. I mean, the demand depends on the price at the enterprise, and this price at the enterprise will depend on the demand of the electric vehicle, and so on. So means that in the optimization problem which you formulate, there will be an additional variable which comes into picture. So basically, third point, I mean, because of this, the computational complexity will increase. I mean, we will come up with an optimization problem which is very big. I mean, with large number of constraints, with large number of binary variables, I mean, these binary variables are because of the routing constraints, whether the electric vehicle should move to this customer node or not, and even whether this sources has to be selected or not, and even the electric vehicle battery charging discharging constraints, I mean charging discharging binary variables are present. So this optimization problem comes out to be a bit complex. So one way to solve this is like we can decompose the problem into two different optimization problems. Okay, so the main block which I have mentioned, like the detailed formulation is given in the paper. So I have not written the 30 sets of equations, here. So we are splitting the problem into routing and procurement cost optimization, and we are solving it iteratively for more faster solution. So basically what we do is like we first solve the routing optimization, then we get the routing information. We share this routing information to the procurement cost optimization block, which will only involve the those part which which will optimize the procurement from the multiple sources, and then the cost of procurement from at the enterprise will be shared back to the routing, and we do it iteratively till very less cost difference is observed between the consecutive iterations. So this cost difference is like the cost difference in the enterprise cost itself, the enterprise purchasing price. And finally, when we have a low cost difference, then we will publish the results. That is the final solution which we get. To solve this optimization problem, we can go to conventional algorithms, simplex algorithm. There are many ways to solve this algorithm. So solve this optimization formulation. So one approach which we have used for a faster computation is the genetic algorithm. We faced some issues with the conventional methods, so we went to a meta-heuristic method. So genetic algorithm is one meta-heuristic method which we selected. So here we have defined the fitness function based on the objective functions which we have formulated for the two different blocks. So we have split the genetic, we have split the blocks into two when we have run the two different genetic algorithm blocks, one for routing and one for energy procurement. And then we have followed the same block diagram. In the sense we have followed the same iterative loop. So basically, like we test this algorithm, on an enterprise which is located in India. So we have some values like, the enterprise is very large. In the sense it has 19 megawatt hour demand. Basically, it has that much contract demand, basically. And then we have a solar capacity which is located, 1 megawatt hour solar capacity which is located at that plant, at that enterprise itself, and an external solar PV as well is present, that is 12 megawatt hour. And most of this routing network contains 75% customer nodes, and the remaining are charging nodes. Charging nodes are those which from where we can, where the electric vehicle can just charge the electricity from, it can charge its battery from there. So basically what we can observe is that there is like different sharing among the different sources. So like we have some particular allocations to retailer, market, captive solar plant, and external solar plant as well. So like the captive solar plant is preferred more because its cost is lower when it is located at its own site, while the external plant we have taken a like slightly higher prices compared to its own plant. So its allocation is bit less. So overall what we see is like there is allocation in the different sources, and so there is a reduction in the effective cost. If it was only to go to the retailer contract, then the cost would have been higher. Then we can see that on the last plot, I have shown the computation results for large number of EV set. So we were facing some issues with the conventional algorithms, like using the conventional linear or MIQP solvers. So here, when we are using genetic algorithm, we were able to solve this problem for even the large number of electric vehicles and even the large number of the routing networks as well. So that we have shown, and most of the times we have obtained, the maximum computation time we have obtained is to be 12 minutes for 100 EVs. It means that this is per iteration. So like this problem has been, the problem is being solved in 4 or 5 iterations. So it would solve like in around an hour or so. So basically the thing is that, using genetic algorithm, we were able to solve this problem, as compared to the conventional algorithm. And the computation time is also very less when we are comparing it with the conventional methods. And in terms of procurement cost reduction, in terms of the procurement aspect, we were able to reduce the cost also of the overall, the enterprise electricity bill were also reducing, like say somewhere around 5 to 10% compared to when it is going only to the retailer. And even the EVs were able to help in like to charge and discharge, like in a sense it were able to charge more than the required for the routing, and then discharge to the demand when it is actually available at the enterprise and when it is not routing in the transportation network. So this is all. Do you have any comments or questions? Like, yeah. Thank you.
Hello. I was wondering when there was this slide where had this training loop where you were optimizing for, yes, routing first and then procurement. Was there any reason why you chose this order?
Okay. Yeah, I mean, it's more easy to solve the procurement cost optimization when you are having a routing information available. I mean,
Sure.
yeah. I mean, if you reverse this, like then you will have to assume some things in procurement cost first. I mean, yeah, okay. So in this block, you have to assume at this moment, like if you are taking this, I mean, this first. So we have less assumptions here, less initial assumptions, then this block. I mean, here we have to assume a lot of things about routing. So it's more easier to.
Yeah, I guess I'm a little stupid about, I don't know what exactly the procurement process means. Does this mean how you get the energy into into these EVs or?
No. Okay. Sorry. I mean, so basically this procurement cost minimum optimization is for procuring the electricity for the enterprise. I mean, enterprise like this Dragon hotel itself is an enterprise, for example. So we have these various loads, right? I mean, the lighting and AC, these all HVAC loads as well as computer loads and so on. So this, I mean, there will be some net demand for this enterprise over the time horizon. I mean, so that is what we are procuring in this block. So this also involves the electric vehicle load at times, but we really don't know whether the electric vehicle is going to charge from here or from the charging station. It will depend on the routing optimization results actually.
Have you seen with this like cost difference loop that you find it to have like a maybe if you're some sort of you said some sort of genetic training where maybe you create like a varied or a variance of different types of methods or optimization methods. Oh, is this usually like a very stable method for this? I would like to see maybe how the cost difference like degrades over time. Is it usually like a
Okay.
very linear cost difference decrease, or how does that go?
No, it's like this.
Sure.
It's like
So it's very stable most of the time, right?
it is quick actually initially, and then it's stable in 2 3
You've
iterations.
never
Yeah.
seen any wild variance in
Not
cost
yet.
difference?
No. I mean, in such a problem, it doesn't seem to arise like that.
I
What I
see.
understand. Yeah.
All right, thank you.
Sure.
Any other questions? Okay, let's thank the speaker again.
Okay.
Thank you.
Thank you.